So we have seen how we can add and subtract vectors using a geometrical approach by drawing them as arrows and use the technique we call head to tail. We also seen how we can take a vector and multiply it by a number in a geometrical sense by having our vector and simply scale it in length by the factor we're multiplying by. However, often we will see in class vectors described in an analytical form, which means we're giving the components of the vector like a x value, y value, or maybe even z value if you're three-dimensional, that makes up the vector. So in this video here and these notes here, we'll just go through how we can do the vector addition, and subtraction, and scalar multiplication when we have them in analytic form. And we'll find that it's actually probably a lot easier or relatively straightforward compared to maybe even the geometrical approach. A little bit more analytically informative, or we say quantitative informative, I guess. So let's start with a vector addition and subtraction. And the nice thing about this here, when we write vectors with x and y and z component, if you think about an x, y, z coordinate system, then those axes are perpendicular to each other. And this is really a key from linear algebra. And it means that those directions are what we call linearly independent. What it translates into is that we can treat x, y, and z components independently. So when we're adding two vectors together, we're going to simply add the x component together by themselves, the y components together by themselves, and if there are any z components, we'll add those together by themselves as well. So here we start with an example. We have two vectors a and b. They have x, y, and z components, and then when we add those two vectors together, we treat those components individually. So we simply take the x components. They both have x components that equal to 2, and to find the combined x component, we add those together. So it's 2 plus 2 give us 4. Similar, we get 3 plus 1 give us 4, and we have 4. We add negative 4 give us 0. So we just treat them like number arithmetic, which is nice. So the result of adding those two vectors together will be 4, 4, and 0. So relatively straightforward, right? If we were to do subtraction, instead of having addition in here, it will be subtraction. So if you were to subtract vector b from vector a, it will be 2 minus 2, that will be 0. It will be 3 minus 1, that will be 2. And it will be 4 minus the negative of 4, which will give us 8. So it will be 0, 2, and 8 will be the result of that vector. So here's just a general rule written in more like a general component form, and just highlighting that the sum and subtraction follow the same rule. We apply them to the components individually. So there's a box for you guys to practice or test your understanding of it. For multiplication with a scalar, it's the same. The scalar is going to be multiplied into each component of the vector. So again, this is the analytic approach. So if we have a vector A that has components 2, 3, and 4, we have to multiply by 5 onto each of those components. That's 5 times 2, 5 times 3, 5 times 4, give us a new vector of 10, 15, and 20. Not much magic there, at least hope to. The general rule, take each component, multiply by that scalar. So the next two boxes is kind of a chance for you guys to check your understanding of this point with vectors. It is mixing a little bit what we learned from the beginning of vectors with position vectors. Box 2 is more specifically with the multiplication, but also addition, and also going back to the geometrical approach So you can compare both the geometrical approach and the analytic approach and try and see if you can explain why those two give you exactly the same result, but the representation is different. In box 3, we really just trying to give you a problem where you can kind of summarize what you learned throughout the vectors experience.